Hello friends, this video on electrochemistry part 12 is brought to you by examfear.com. No more fear from exam. It's derived this whole Nernst equation, right? See, Nernst equation is based on equilibrium constant. It is based on equilibrium concept. Yes, it is based on the equilibrium concept. So let's take a reaction. A moles of capital A plus small b moles of capital B reacts and some n electrons are transferred. You get small c moles of capital C plus small d moles of capital D. This is the reaction, let's suppose I have. Right? So at any point of time, if I want to find Q is nothing but what? C, capital C into concentration of C, capital D into concentration of D, small d, by capital A, concentration of A, capital B, concentration of B. That is the value of Q at any point of time. Right? And at equilibrium, we know that at equilibrium, Q is equal to K. So what you get at K is nothing but the value of Q at equilibrium. Right? So if Q is less than K, so if Q is less than K, the reaction will move in forward direction. If Q is greater than K, the reaction will move in backward direction. So this is something we know, equilibrium concept, right? The value of Q is nothing but concentration of reactant by concentration of product by concentration of reactant at any given point of time. And at equilibrium, the same value Q becomes K. Right? So if Q is less than K, the reaction moves forward direction. Q is greater than K, the reaction moves in backward direction. Also, we know one more critical equation, that is delta G is nothing but delta G naught plus RT ln Q at any point of time. Correct? This is the equation I know. This is equation, let's suppose 1. This is equation number 2. These, we know that. Right? The Gibbs free energy change is the delta G naught plus RT ln Q. Right? So in case all these species are 1 molar, this A, B, C, D all are 1 molar actually, all are 1 molar if you see, all are 1 molar, this Q becomes 1. ln Q becomes 0. So delta G becomes delta G naught. Right? So case 1. All species 1 molar. That is what we have seen till now, right? And delta G becomes delta G naught plus RT ln 1. That is nothing but delta G becomes delta G naught. That is what we have seen. Right? Now let's talk about this is delta G, right? This is all we know. But we have to find the electric potential, right? So what is electric potential? We know that electric potential is nothing but work done per unit charge to bring a unit charge from infinite distance to point of interest. Let me write this definition actually. Electric potential is work done per unit charge to bring a unit charge from infinite distance to the point of interest. The point I am talking about, right? From some infinite distance, I am bringing it to some point Q, right? So I can write that work done, since it is per unit charge, right? So that means nothing but electric potential into total charge of n molecules. Total charge of n mole of electrons actually. Why? See, because I am trying to bring some n moles of electrons, right? This n moles of electrons are getting transferred here. So what is the work done in this? I have to find total charge on these n moles of electron into electric potential, correct? Because there is a potential, you know the electric potential of that. So that is the work done by the system, correct? Because for this system, let's suppose E is my electric potential and Ne is the electron, N is the number of electrons that is getting transferred here, right? So we are, and we're using n moles actually, because we'll not talk about the one number, right? We'll talk about, because A moles, B moles, C moles, D moles, then it's n moles by default. So we have to first find the total charge on n moles of electron. We'll multiply with the electric potential, we'll get the work done by the system, correct? So first find the charge on n moles of electron. Let's do that. So first find the charge on n mole of electron. See, we know that charge of one electron is what? 1.60219 into 10 to the power minus 19 coulomb. One electron, right? So I have to find charge of 1 mole of electron. It will be what? The same number which we have got, 9 into 10 to the power minus 19 coulomb. We will multiply with number of electrons in 1 mole. That is nothing but Avogadro number. That is nothing but 6.023 into 10 to the power 23. Because we know that if you talk about 1 mole of electron, that means you're talking about this many electrons, correct? And that is nothing but 96500 coulomb. And you call this as 1 Faraday. So if charge on 1 mole of electron is 1 Faraday, charge on n mole of electron is what? N Faraday, correct? So now we have found the charge on n moles. So that is nothing but NF. We know this guy. And what is the electric potential? E. You know this also, right? So the work done is nothing but NFE, correct? See, work done is W. Work done is W. Electric potential was E. We have just assumed E is the electric potential. And the total charge, E is the electric potential. And the total charge on an electron is NF, right? So work done, this work done is electrical work done. Work done, electrical work done is NFE. But in this case, in this chemical reaction, right, in this cell, we have only electrical work done. There is no mechanical work done, correct? Because the pressure and temperature is constant, right? So net work done is nothing but electrical work done, correct? So my delta G, let me check. So my delta G here will be equal to what? Work net, and that is nothing but minus NFE. Why? Why minus? Because the work is done by system. Work is done by system. See, nobody is doing work on system, right? System is doing the work. The reaction is happening on the system and the system is doing the work. So delta G is minus NFE, correct? And with this reaction also we know that if delta G is minus NFE, delta G naught will be what? Minus NFE naught, correct? Instead of G will put G naught, instead of E will put E naught, correct? Now let's put this value in this equation. So we'll put this delta G and delta G naught in this equation. So what this equation will become? So delta G will become minus NFE. Minus NFE is nothing but delta G naught, that is minus NFE naught plus RT ln Q. So let's make this equation a little better by dividing whole side with minus NF. Minus NF, we see this is common. So we'll divide this by minus NF, minus NF, minus NF. It's cancel. So with this what you get is E is nothing but E naught minus RT by NF ln Q. So that is my Nernst equation. So if you see, it is derived from this Gibbs energy equation. Correct? And if you don't want to use ln, you can use this equation where E is nothing but E naught minus 2.303 RT by NF log Q. Why log Q? Because if you're seeing here, instead of ln, I'm using log. I know that 2.30, 1 ln is nothing but 2.303 log. You can use any of this equation. So this is the derivation of Nernst equation. So if you see, Nernst equation which we have found has a lot of variables. E is equal to E naught minus 2.303 RT by NF log Q. Right, this is what we have found. But most of the experiment the chemists do, they do at 298 Kelvin. And there are a lot of constant here. R is constant. If assumed temperature is 298, this becomes constant. And F is constant. And 2.303 is constant. So let's put all the constant and see what you get. So we'll be putting TS 298 Kelvin. R will put 8.314 joule per mole Kelvin, and F we know is nothing but 96487 coulomb per mole. So let's find the value of this whole thing. This is my variable actually. Right, let's find the value of this. This becomes 2.303. R is 8.314. Please note the units. Joule per mole Kelvin into temperature, right, 298 Kelvin by NF. N is nothing, sorry, NF. F you have to write. F is 96487 Kelvin per mole. Kelvin cancel, mole cancel. So what you get is 0.592 joule per coulomb, and joule per coulomb is volt, so it becomes 0.0592 volt. Right, this is what the value of this comes out to be. Right, so I can rewrite this as E naught minus 0.0592 volt by N log Q. Let's volt be here. The whole thing will be in volt actually. That is one way of writing this equation, because most of the reactions happen at 298. So instead of writing all the variables here, we can simplify this equation. Please note, this equation is only for reactions happening at 298 Kelvin, that is room temperature, ST. Thank you. Visit examfear.com to watch more videos, attempt free online tests, get free study materials, find tutors and mentors, and much more. Thanks once again. Examples on